Yes. All right, great. Fine. So let me first share my screen. Shubhajyoti, maybe can you accept them as they come? No?
Yeah, sure.
Yeah, great. So I hope you're able to see my screen, right? Hello?
Yeah, we can.
Okay, perfect. Great. So yeah, I think we have about not 2 hours to kind of discuss about the majorly AI, ML, and data science part. But for the first half an hour, maybe we'll just talk about some of the processing aspects of it. So in terms of a tool called Compose. So let me first give you a brief agenda of where we are and what we're going to talk about today. So if you remember, probably some of you might have joined earlier sessions as well, where there was smart product development and all the different areas that was covered yesterday. Me and Chandra Kumar, we both covered on the model-based design approach using embedded programming as well as the Activate for to some extent. So there we spoke about the 1D model-based design where you can connect different physics using 1D mathematical blocks and then build a system and add controls, deploy them to microcontrollers, and so on and so forth. So that's one aspect that was discussed yesterday. So today we'll be majorly covering on the machine learning, AI, and the data science aspects, which will be covered by my colleague Shubhajyoti. So for and to begin with, we'll talk about Compose as well. So Compose actually falls along the same bucket of model-based design, but Compose being a mathematical scripting tool is more of a you can do some data processing, understand the data, visualize the data, and we'll talk about the model-based design. A quick recap of that probably, and then a good introduction of Compose and all the features which are part of Compose and some of the use cases in different areas. I'll just cover it shortly. So these the bold ones is what I'm going to cover in half an hour, and the next 1.5 hour, Shubhajyoti will talk about our entire platform for machine learning, data sciences, artificial intelligence, and so on. So that's the whole agenda today. So let me quickly recap on what we did yesterday and how Compose is connected to it. So as you know, if you talk about a mechanical system, an electrical system, or an electronic systems, generally when we look at modeling them, so we usually do it through a three-dimensional process. You do it through a CAD, and then you do a finite element simulations or in different fields. And that is what the 3D aspects to it. On the middle layer or the middle row, we have 1D, which is more of the signal-based connections, or basically, we connect each block together and build the entire system, just like you're seeing here, for example, a simple car model with an active suspension, for example. And this is what we covered yesterday. This is the platform of Activate, and we bring some springs and dampers and connect them together and understand the acceleration mathematically. The same thing applies for even motors, where we can do a motor controls and virtual controls or physical controls, where we can bring in all these math blocks. And same thing applies for electronics as well. The other aspect is what we call 0D, which means a pure mathematical based approach, which means that you just have for any engineering problem, you always have a mathematical equation associated with it, and that's where we are going to focus today, and that's what Compose is all about. So you can be suspension motors or electronics, you can pretty much do a mathematical equation using basic equations. So um, so in terms of the model based design, there are essentially three tools: Compose, Activate, and Embed. As we covered yesterday, Activate was on the multidisciplinary system simulations, which means you can solve thermal, integrate with hydraulics, connect them with signal-based models, or mechanical models, or electrical electronics models, and so on. So the entire vehicle or entire platform can be all connected together and solved in a single simulation software. So that's what the Activate is all about. Embed is more on the motor controls, or embedded programming, deploying to microcontrollers, C code generation, C code deployment, and so on and so forth. So Compose is very similar to Octave or MATLAB that you're pretty much used to, which is an advanced mathematical solution for scripting and as well as processing and so on. Okay, so we'll quickly jump into Compose today. So Compose is a one in class environment for all kind of math calculations. It could be some kind of developing of algorithms or computation and so on. So if I look at Compose in four broad areas in terms of its capabilities, uh, these are the four areas. First, it has its own wide variety of mathematical libraries. So if you want to mathematical equations, you want to do processing of your signals, test data, or any other kind of data that's coming in, you could use Compose, where you can use all these different libraries like linear algebra, statistics, differential equations, signal processing, control systems, polynomial fittings, optimize numerical optimizations, and so on. So all these form an aspect of using all different kinds of math to do the required engineering or required processing of the data and so on. The second one is its built-in CE readers, which is one of its key USP and a key differentiator. So since we have our own solvers and readers for finite element model, we also have capability in Compose today to read all kind of results, test results or CAE results, and be able to read them. Data can be stored and manipulated and all that. So another main differentiator of Compose is the multi-language environment. So what it essentially means is today majorly Compose, the main languaging platform of Compose is Open Matrix language, which is called OML. So this open matrix language is, we can say, 99% similar to, if you have used MATLAB or Octave, it is 99% similar. So the syntax does not really change much, but it's based on open matrix language, and it's kind of a syntax compatible with MATLAB and Octave. But along with that, which is its main, language, it is also compatible with Python. So let's say you have some code today, which is based on a mathematics, that is a MATLAB code or some kind of Octave code, and you also have a Python code. So you can always combine these two together into a single platform of Compose. So or not just Python here, even if it is TCL code and R code, you can all combine them all together and simulate it at a single go. So basically that's why we say it supports multiple languages together, and it is one stop environment for all the different languages. So most of the students especially focus a lot on Python these days, along with, of course, the OML language or the MATLAB language. And usually we've seen that these are easy to combine, and the data can be exchanged easily, and you can play along with both of these languages together. So that's one of the advantages. And of course, all the plotting capabilities of 2D and 3D to provide the analysis and so on. So typically, if you look at Compose for let's say a CAE, so we have seen significant benefits, and I've just put across two or three main major customers who have shown a significant benefit by using Compose today. So let me give a quick overview of capabilities. So one is its advanced mathematics. Second being the ability to solve various multiple order differential equations. Third being the data and signal processing aspects. The optimization, numerical optimization, it has its own set of portfolio, like you can do a genetic algorithm, nonlinear equation solving, and so on. and advanced visualization, be it 2D or the 3D visualization that you're seeing here, and of course the integration with the CAE area. So if we were to dig a little deeper on the main capabilities, let me start with maybe the processing, because I think that's maybe the more important one today. So we have inbuilt libraries for signal processing per se, which means that all kind of data processing, filtering, conversion from time to frequency, or so on, and understanding the different attributes or properties of a signal. So all those can be done using the signal processing toolboxes. So that's pretty much there as part of this. So as I mentioned, there is what we call connections with various other tools like Python, TCL, R, as well as it is pretty much interoperable with MATLAB and Octave. So today, if you have a MATLAB code, you can pretty much copy paste the entire contents into Compose and then run them. Or if you have an existing Python code, you can pretty much copy, and in fact, since Python is already there, you don't have to worry about anything else. You can just load that Python file and then start running in the Compose environment. Of course, same way the math engine in terms of polyfides, differential equations, linear algebra, and in terms of the graphical interfaces, as you know, like in Compose itself, we can pretty much you may need to sometimes create the user interfaces, for instance, to create some kind of applications for your projects, or for anything like that. So you write a script, but it's very difficult for everyone to keep changing, modifying the scripts, and that's when a graphical interface would be really helpful. So that's where Compose also supports a lot of commands for creating a user interface and supporting that. And also you can develop your own library. For example, we have been developing our own library for, let's say, machine learning, or vibration toolbox and so on. And those custom libraries can be developed and stored in Compose as well. So all those are pretty much possible. So this is the environment, the know-how and the look of Compose today. So if you see here, especially if you have been working on, let's say, a Python IDE, or MATLAB and so on, you might find that very similar. So we have an editor where you can write your scripts, okay, and a console or a command window where you can understand and visualize the results and get the results in terms of data and so on. A browser from the current directory, and of information about the project in terms of all the plots or what are the variables are there and so on. And there is a browser here, which basically tells you all the different variables, their values, and the kind of type, and what is the situation, and so on. And of course, all the different authoring and debugging options, which are usually standard, are all available, like starting debugging, and over and in, and so on and so forth. So all these different, this is a typically environment for the Compose. And of course here, if you see, this is a .oml file, which is the open matrix language. And if you noticed here, the language is very similar and very intuitive, so you can easily understand all the different commands, especially if you have used in past some of the other legacy tools. Um, so I have a couple of user stories on Compose, but before going there, maybe if you have any questions on this so far in terms of its capabilities, or anything that you want to ask, you can, or if you have anything in the chat window, maybe we can have a look. So any questions? Okay, so let me then go to the some of the user stories. Uh, I hope you are able to hear me, right? Or Shubhajyoti, can you confirm? Okay,
Yeah,
fine.
yeah,
Yeah, okay. So, and then in that case, let me just quickly go to user story. So, if you have any questions and you want me to, talk about it, please, feel free to interrupt, or you can post it there as well. No issues. I can answer them whenever you want to ask them. You can please ask them. So, in terms of user stories, the first one is on the NBH side of things. So, for example, typically, if you see, this is the user interface that's created with that, and so this is a kind of workflow that you can create. So, for example, if you have a test file or something, you can pretty much develop this kind of an interface, and it supports all the kind of user interfaces. For example, entry, a table, there's some kind of entry boxes and buttons and so on and so forth. So all these different aspects are pretty much covered. So everything, the mathematics is all happening behind the scenes. So um, that has to be taken care. Right. And so this is typically the environment for compose, where this process could be, was usually done through manual process, and now we can see that, we developed an application kind of a thing where you can pretty much select everything. You will get the data instantly, and you can start and end, visualize the results, and so on and so forth. So that's the typical advantage of developing a complete application using compose, and everything behind the scenes is mathematics that is taking or driving the things. The other one could be on the, let's say, of course, the application might be different. The here one of the application is on the processing of the data that's coming out of roads. So generally, you all know that, when automotive vehicles are usually tested, there are various different types of roads for which it has to be tested: Belgium pavement, cobblestone, and various other road conditions. And for each of the road condition, uh, uh, you know that gets excited onto the tires, there is a particular curves. And when we get the data, we might have to process the data and make sure that those data is smoothened, and because that's not the raw data, cannot be typically used for our simulation. So of course, this could be a different application, but the processing applies, and you could use and reuse the processing as such. So again, for this application, we had created a user interface. It's up to us if we want to create or not create a user interface. So we just had created a typical track, user interface to kind of take us through the entire process. So yeah, this is the signal that's generated from the channel 1 or something, and the whole road in terms of, let's say, 25 or 24.5 seconds of data, right? So then we can do all kind of processing. So here, for instance, we are trying to filter the signal from 20 to 70 hertz, and then we'll display the filtered data and understand the peaks, the behavior of the peaks, and so on. We can also divide, we can export the data in kind of a CSV file or something, and we can pretty much do a level crossing or understand the various permutations and the combinations of the signal. For instance, if you see here, I'm dividing the entire signals into 20 up and down. So each data is divided into multiple such levels, and for each level, the user can also understand using the different algorithms that are inbuilt. So, and these are the CSV files that are kind of getting generated out of that. So we can read and write CSV, Excel sheets, and text files, and various other file formats are pretty much readable and writable. And we can extract all the various parameters or the data features out of this particular signal. So here we have a simple 5 or 6 basic parameters. For example, min, max, mean, standard deviation, counts, and so on. Of course, we can identify many more such parameters, like it could be an RMS or any other mathematical attributes. The signal can be pretty much extracted. Probably those could also be used. Once you extract them, you can also use them for further ML side and data sciences and so on. So So that's about this. The second area of how I just put this because it's a completely different scenario as well, where for example, if you're looking at filtering processes or processing or signal processing, it could be any signal, right? So here we have a raw ECG data. Okay, this ECG data is being read from an Excel sheet now directly. So and once this data is being read, we can create our own low pass or a high pass filter. For example, if you see that we have plotted this ECG data, and once that's plotted, you're doing a Butterworth filter, which is again a standard command which is available there, and then doing all kinds of filtering processes. Once this filter is done, and then you are writing back this data again into an XLS, right? That is an Excel sheet, right? So, and of course you can compare the um, you know this original versus the filtered data. So original being the blue and the filtered being the green signal. So you can compare how the results are varying. So this is a very easy comparison parametric studies, creating and processing the signals. It could be low pass filter, band pass, high pass filters, and so on. So all those can be pretty much done. Okay. The other aspect is the digital data compression as well. So for example, um, again, the same library of signal processing was used, but it could be for a different application. So for instance, if you're looking at a transmission of satellite data from the space and ground to the ground, we really need to produce smaller data packets so that it which kind of requires a less time for the transmission, and the signal processing functions will easily compress the data without losing the data. So that's very important, especially today. This could be from the satellite, it could also be from the cloud platform, it could be sending back to the cloud or receiving the data from the cloud or any kind of other communication protocols, sensors, and so on and so forth. So for everything, we need to compress the data, make sure minimum data is received with minimal loss of quality as well, and that's where the processing is really helpful. So I'll not go into the theory much, but the main function you used here is the FFT, or a Fourier transforms, fast Fourier transforms, which is to basically convert a time domain problem or a time domain signal into a frequency domain, because this is my amplitude versus time. And okay, so when we do an FFT, we get the amplitude versus the frequency data, which really tells us at which frequencies is how the my time signal is behaving, what are the different frequencies that are getting actuated. And of course, once you have the amplitude versus frequency, you can also compute the power spectral density, which really indicates the entire power of the particular signal at the different frequencies, right? So um, let me maybe quickly go into the you know I might skip some of these slides. Let me just go to the compose itself. Okay. And I can show you this digital data compression as a code, and in the compose itself. So okay, so here we have, this is the compose environment. So if you noticed here, like as I was mentioning, you have a variable browser and a demo browser, a property editor, and all those different aspects are there. And in here you have various file types. It can be OML file, a TCL, or a Python file, and a text file, and so on and so forth. So all these different aspects of file reading can be pretty much done. So here on the right hand side, you have a file browser, and there is a library browser, which basically indicates all the different libraries which you will get as part of compose. Okay, so here if you see, since I have a py file, Python console is also opened up, and I can pretty much write a Python script here as a command window, or start writing them here, and create the codes here. In the same way for OML language is anyway based out of a matrix language, so you can pretty much keep writing the OML console windows. Here there are a lot of functions that are already available for this particular aspects, and you can always click on this and get the visualize the results as with the various views and so on and so forth. So let me just delete for now. So in terms of a library browser, so there are about 1,000+ functions which are directly supported. Of course, this does not include Python. So if include Python, everything in terms of that can be supported. So right. So only in terms of OML per se, these are the different libraries. So I'll just quickly go through major libraries, like for example, calculus. You can do a calculus things. Um, Computer vision. We have a big library of all kind of options for computer visions, from adding a CV to a blur to clearing, and as well as to divide or erode or distance understanding, get the structuring element, median blurring, morphology, resizing, rotating, or normalizing, multiplying, morphology, EXCV, or subtracting, threshold CVs, saturations, etc. So all these different options to play with your image or videos are pretty much available. Again, in terms of control systems, we have various equations for transfer functions and control systems and so on, and differential equations, various like Rangakuta method or ODE 113, and different such options are available. And in terms of linear algebra, again, all the basic commands from determinants to inverse of matrix and so on, and you can do all sorts of such things. And in terms of Python bridge, for example, if you have a variable today which is a, you can pretty much export them to Python. So this can be run in there, and you can visualize the results here as well. So that's how the data transfer happens, and you can seamlessly run everything together. So that's the advantage. Next is again signal processing. So various types of filters, FFTs, FFT2, finding the peaks of a signal, frequencies, different windowing techniques, inverse frequencies, upsample, downsamples, PSD signals, and all those are available. Again, statistical analysis, you can do various distributions like beta CDF, beta fit, identifying the bins, cumulative distribution, error or detrending, correlation functions, and various other for example, gamma or kurtoses or log PDF and so on and so forth. Various distributions like uniform, normal, Poisson distributions are all available, which you can pretty much use. So these are different basic libraries that are available. So along with that, if you want to look at the Python as well, so there are multiple libraries inbuilt and available here, starting from Python to all those different libraries are with their individual versions are available. Of course, you can also install and install your own on top of this, or you want some more libraries, you can always install, and so on. So this is the entire look and feel of Compose. Let me now go to the data compression library. So here we have a okay. So if you see here, we have a particular you know a code here which would basically get the file and read the text, and we perform an FFT, as you can see here. That is the fast Fourier transforms, and then we're going to plot them. And of course, once that is done, we are using a PSD function, which is p welch, and then we are dumping in the results in the plot here. And these are all the functions for labeling and developing a semi-log file and so on. So let me have a hand window of, let's say, 10, and let's say I give a cutoff frequency and a Butterworth filter of 5. So this is how the results are coming. So let me just say undock, so that I can avoid the docking and I can visualize the kind of results. So here, if you see, the input signal is a original signal blue, and then we have filtered the signal, that's the red one. And that filtered signal, we have developed a spectrum of that filtered signal that you see here. And then we have done a power spectrum of that signal, understood the magnitude of the digital filter and the phase of the digital filter that's getting created. So these are some of the basic things which can all be pretty much done. This is what we have in terms of data compression per se. So if you see here, the data is lighter, from the original signals, you see that the data has become much lighter in sense. So that's the whole processes which you can follow, you know, um, to kind of compress the data and visualize. So of course, I have tried to focus all my use cases in the area of processing only, but of course there are many more, which areas which we can cover up to work on these composed platforms. So well, in terms of references of compose, we have been engaged with various companies and developed various use cases and projects we've been working on. So it could be Porsche to Anydim and Hutchinson and Leonard Bayer and so on and so forth. So all these different references are pretty much there. So I think that's it from my side on compose. So any questions before we jump into the main topic of the ML and data science from Shubhajyoti? So if there are no questions, maybe we can jump to the ML aspects. Shubhajyoti, maybe you want to?
Yeah,
Yeah,
sure.
sure. Thanks, guys. Any questions, you can always, uh, write it here and in the chat window, or you can ask me and I can answer them. Please go ahead, Shubhajyoti. Yeah, thank you.
I hope you can see my screen.
Yes.
So I have about an hour. So, I'll be speaking about the application of data science, machine learning, AI, also try and explain how they are differentiated, what are the different sorts of algorithms. So it's mostly general that would apply to any domain. So since most of the attendees are engineers, but they might be from different disciplines as well. And going forward, you might join different industries as well. So, I'll be speaking in general terms, and then, once these slides are over, we can have a quick look into the Knowledge Studio and its, capabilities, applications, and some use cases that we have built. Okay? So yeah, so I mean, starting with the first one, what is like basically, machine learning or data science or deep learning AI. I mean, a lot of these terms are used interchangeably, right? But they hold a specific place in analytics domain. So all of these come basically under the umbrella of analytics. Some people would analyze visually, some people would add an intelligence to it to predict something, and going taking it from prediction, you might have some constraints and all to get into the domain of optimization. So I'll try and explain them to you. Basically, this is focused on engineers. So let's say the way Manoj explained, using Compose or using other even simulation tools, you generate the data. So the basis of data science is the data, of course, and by now a lot of you would be cognizant of that. So let's say we get product design and engineering data, and then we add a layer of intelligence, machine learning or deep learning like neural networks and all, to gain predictive insights. Like with the data, if I see some a particular behavior or a particular pattern that determines an outcome, I can try and segregate that pattern, build a good model and try and predict like how the outcome would be. So if it has rained for the if you have the weather data for last 3 years or 5 years, you can forecast with some sort of accuracy whether it's gonna rain tomorrow or how is the humidity gonna be, or things like that. So it can be applied to basically any domain. And these are some applications in the engineering domain. So basically, since data science is kind of it goes hand in hand with programming as well, because when you get the data might be collected from anywhere. It can be collected, let's say, if you are into retail domain like Walmart or Amazon or Flipkart, it can be from the data can be generated at the point of sale, and the data is maintained in lakes. But let's say you are working for an engineering workshop where the data is coming from sensors. Sometimes data is hand recorded. Sometimes you get printed data in PDFs. So once you get all that data, you need to do a data frame manipulations, for which there are several Python libraries available like NumPy, Pandas, and even in Knowledge Studio, you can use. Knowledge Studio is basically our platform for data science. So in Knowledge Studio, you can import Python libraries for data manipulation, or you can use its own native functions, just the way Compose has. Knowledge Studio also has some of the functions available. So once you have the data in a row column format, where every column means a feature in your data set, and every row is a record in the data set. So in traditional programming, you hardcode instructions to it. Like if I get this data, I write some rules, and those rules are executed and you get an output, right? So that's a rule-based approach. But in machine learning, you can see the difference is this kind of looks like a feedback loop, right? So once you get the data, you understand distribution of the data, you understand how how the data is distributed for every feature. Like if it's a car, a data of a car, and you get the height, weight, you get the kind of transmission, the kind of engine, the capacity, and and a lot of details about the car, right? How the engine is aligned and all that. So all of these are features of that car. So if you have data for 1 million cars, you will have all these features, let's say 20 features for all the million cars. And some of them might belong to a particular model, groups of cars may belong to a particular model. But once you analyze the data, you'll find, a pattern in the data. Like, if the data is for breakdown, you may find that, okay, Ford Mustangs with this year's make, with this bore weight is failing, regularly. It might be a design issue. It might be something to do with the assembly line. So, I mean, that pattern you'll have to, look for through machine learning, so that you can predict. You can, when a failure occurs, you can at least with certain certainty, well in advance, so there, if it's a failure detection problem or a predictive maintenance problem, you can't wait for the failure to occur, right? So using all these features, you find a pattern and you try to predict with some probability that this part might, might fail in the near future, so that you have enough time in your hands to, take corrective measures. And this is only possible if you have a lot of failure data from the past. Okay, so some of the applications of data science, as I said, it's a domain agnostic. So it's applied to a lot of domains, like from your speech recognition, image recognition. A layman user, a regular user, who probably hasn't even heard of data science. They use or they are end consumers of machine learning algorithms when they are, let's say, using a phone or when they are on social media, like on your Instagram, your recommended videos, your recommended searches, your recommended items on a shopping app. All of these are a result of machine learning. And the organization uses your past data and your demographics, like if you are a male or a female of a particular age, with a range of income, they would recommend something for you. And then if based on your clicking habits, they would recommend something else for you. So the a common consumer is mostly let's say exposed to the AI bit of it, the layer that comes with an application, right? But in banks, in financial institutions, they would use it differently, like fraud and risk detection. So the end user would probably won't even know, when you have a fraudulent activity on your banking account, your bank would intimate you, right? But they would be using all sorts of algorithms, and then again based on your past data and past behavior to to immediately inform you that there might be a fraud happening on your account, and so that you are aware and you can confirm back to the bank that if it indeed is a fraudulent activity or not. Similarly, it has applications in gaming. It has applications in price comparison websites. Like in certain websites, it would be dynamically priced. So let's say you are going through a set of clothes to buy, right? Or certain appliances. Also, let's talk about mobile phones, right? So if you're looking to buy a particular sort of a model that's very high in demand, you would see the prices not dropping, or it might even increase sometimes. That's called dynamic pricing, and that dynamic pricing algorithm is patented. Every a big seller have their own patented algorithms, right? But the basis remains the same always. So similarly, recommender systems is what I said, what you see on Instagram or Facebook, So let's say if you're talking about Instagram, the way it works is, the way it generates revenue is how long are you on the app, right? So even if you're not buying anything, even if you're not shopping over there, it would still earn if you are on hooked onto the application, right? So since their motive is to keep you hooked on, they would recommend or suggest videos that they feel would match your interests. So that's also one application for recommender systems. So yeah, these are some of the applications. So coming to differentiating between ML, DL, and AI. So artificial intelligence is the broader thing. It just how to say it, like the human beings have the ability to let's say decide right or wrong, and when you enable the machine, or when you enable an algorithm to take that decision for you and feed a lot of data to it, I mean, I guess that's the point where it becomes artificial intelligence, right? So within artificial intelligence, there are machine learning algorithms, there are deep learning algorithms. So using machine learning algorithms, there is this segment of Bayesian statistics that's based on probability. So based on probability scores, you predict that tomorrow's humidity is going to be 70% or less or more, or let's say what would be the how many quantities of a particular model of a motorcycle would be in demand. So let's say whenever let's say Royal Enfield or any other company would come up with a new model, they'll always try to predict whether there'll be a back order on this model or not, so that they can meet the demands, right? So whenever they launch, they tease a new, upcoming model of a particular motorcycle. They would try, to predict the demand for it. So when they have forecasted the demands, that is when they would, try and optimize their production. Because if they produce too many, there would be a problem of storage, right? Because they can't send it to the showrooms, and they would need to pay for the storage in the warehouses. And if they produce too less, if there is a huge demand of particular vehicle model, and if they're producing too less, they would probably be losing out on the revenue, what they would make when they sell that particular model. because the customer might lose interest and move on to a different model. There are so many available out there. So, depending or by understanding the data and the buying patterns of the consumers, that's what they try to predict. And deep learning is part of machine learning, where it doesn't depend that way on Bayesian statistics. It depends more on neural networks, where you create layers of neurons which tries and understand the pattern in buying. The a good thing about deep learning is, firstly, you can apply it to basically anything, and the major applications of deep learning are in image recognition, voice recognition, and video processing, things like that. Because it can take huge amounts of data. The data works in a matrix format, but it's non-explainable. So let's say when you apply for a loan at a bank, the bank might use deep learning to identify customers. But when you apply for a loan or a credit card, it cannot run a deep learning algorithm to tell you that whether you'll get it or you'll not get it, whether your application is processed or rejected. Because these institutions basically work on a more transparent way, I would say. And they would have to explain to you, and they would have to give a score, like like the way your CIBIL score is. They use the CIBIL score and a lot of other details to reject or accept your application. But if it's rejected or if it's accepted even, you have every right to know, like, why did your application get selected or rejected. In that case, since traditional models are explainable, they can tell you, or they can explain to you that what do you need to work on, which would be difficult to explain if they were using a deep learning model. So which is where statistical, traditional probability based statistics come into picture. And moreover, these models are simpler, easier to train, faster to train, do not require graphic processing unit, can be done on your CPU. So both have their own applications, right? And as I said, the way end user sees AI is probably after all these predictive and prescriptive layers. They would be using an application that would probably a speech recognition app, or when you try to contact your bank or a service provider, you speak to a chatbot. And chatbots are definitely improving. And you can see Alexa, the way it trains, it understands the speech, and gets better recommendations for you. So that's how an end user sees the applications or uses it, right? So this is the basic difference between DL, ML, and how it ties up to the bigger AI picture. So yeah, coming to data analytics versus data mining versus machine learning. So as I said, data analytics is the top level. You can analyze the data in Power BI or Tableau. You do not always need to predict something, right? It depends on the organization you're working at, and what field are you working in. Sometimes you would just want to see the results, or how a particular segment is performing, how this particular plant is performing, and what other products it's producing, and how much sales are we making over there. So for this sort of an analysis, you are not essentially predicting anything. So you would probably need to make a good data model, a relational database, and then finally visualize it in Tableau or Power BI. It can be a live dashboard as well, right? But if you're predicting something, yeah, you create models and you continuously improve them, right? So as you see here, data analytics is a process of sourcing, cleaning, transforming, and analyzing the data to find out meaningful pieces of information. So even looking at a dashboard, you can see the major contributors, or the major affiliations of a particular segment of data. And then if you see that sales are being affected by advertisement, advertisement through social networks, through other HTTPS pages, or through newspapers, and you understand how the sales are being affected by each mode of advertisement, and that's when you are that's when you know that, well, these are the major contributors for our sales. So let's build a predictive model, and let's because now you know which are the important variables, and what are the variables or features that can affect your sales. So once you do that, once you try and predict something, that becomes machine learning. So machine learning is the study of computer algorithms that improve automatically through experience. Like the more data you provide to it, the more test data you provide to it, the better it becomes. So in a predictive maintenance scenario, so let's say again coming to an automobile example where you're trying to predict the failure of a part, of a part in the automobile. So in that case, if you have less failure data, so if you have data for the last 5 years where there is very less failure that has occurred, and in like in 1,000 records, let's say you have 5 failures that have occurred. So the machine would learn very little because regarding failures, because there is not much data that's available, right? So the more data you feed to it, the better the algorithm would become. There are several ways to tackle this problem of imbalance in data, but that would be going deeper into data science, like techniques like oversampling, undersampling, generating synthetic data points, and there's several libraries available for that, and those are integrable with Knowledge Studio. Okay. So there goes your machine learning, your data analytics. Your big data analytics would be again very similar, or very closely tied to your machine learning or data science. It's just that big data would include a data lake, basically, where huge data sets would reside, databases, and unstructured data can also reside. And usually the size goes up to terabytes to zettabytes. And so this would be big data. So big data usually is generated at every instance. So as I said, large organizations like Walmart or let's say Amazon, they would probably be working on big data because there are huge transactions carried out every second, every nanosecond, and they would be streaming it all, real time. And so that data would definitely not be maintained in your flat files or SQL DB. It would be probably maintained in MongoDB or big Hadoop Hive data structure, right? So using harnessing that data and to find patterns within that data would be called big data analytics. And big data analytics is again very closely tied to data mining, where you just understand the pattern in the data. You try and create features or understand the features of the data rather than immediately going into predicting something. So it's basically data mining would be understanding the real pattern in data, and a very good algorithm for data mining would be support vector machines, where your data is let's say distributed in various planes, in you know in a 3D or a 4D, in a vector space, basically. And when you see the data from every axis, you can easily segregate the data, right? So this is basically what data analytics, machine learning, big data analytics, and data mining is. So all of these tie up into AI. So basically what you see on the left, data mining and big data analytics are very closely tied together. And then there is your machine learning, which you do on I would say, a smaller data set. Machine learning can also be performed on big data or on a smaller data set. So again, coming to an example, this visual is the example of a classification algorithm. So when you are using machine learning to predict something, you can predict a number or you can predict a class. Like you can predict tomorrow's temperature, or you can predict whether a loan application will be accepted or rejected. If you are predicting a temperature, you are predicting a continuous number. And so the temperature would have a range from probably a let's consider in India, in the southern part of India, it would range from 10 degrees C to, let's say, 40 or 45 degrees C. So it would there would be a range, and you would predict a number in that range. But if you're accepting or rejecting a loan application or a credit card application, or something like that, you would finally be taking a call to accept or to reject. So these are two binary classes. There might be multiple classes as well, accept, reject, and do something else as well. So as long as you're predicting classes, it would be called the classification. So if you look at this picture, it would try to differentiate between an ice cream and a taco. So the first picture and the third picture, the top are for ice creams, and second and the fourth are for tacos, right? So as Manoj had shown in Compose, you can use OpenCV to process your image. You can use Python as well to process your image, and you can add blur. You can do basically everything that you can do with an image. So once you're processing your image, so that the machine understands the background, the edges and everything about the image, so that it learns which is an ice cream and which is a taco, right? So when you add more and more data to it, so the data would be in, again, the picture would be converted into pixels, it would be converted into channels, and finally those would be numbers, right? So when you feed that data to it and you label the data, so let's say I have 1,000 pictures labeled for which is for ice cream, which is for a taco, and I feed that and I use a neural network to, let's say, build an algorithm or a machine learning model. So when I test that model with new images, let's say this image at the bottom, it would, the model output would be a label. Like if you feed the data for an ice cream, it would be labeling it as ice cream or as a taco, and it would give you an accuracy score. Well, with 95% accuracy, this model is saying this is, I mean, there is always a chance of the prediction, not being true, right? So there is always a probability score or a level of accuracy associated with any output. So when you write the a machine learning algorithm, it understands your input features, it understands your dependent and your independent variables, and when you deploy that model, so let's say you deploy that real time, uh, and there are various deployment uh, uh, applications available like AutoML, MLOps, or Amazon S3, or MLflow, or using REST APIs. So when you deploy a model, you just send the input features in terms of matrices of numbers, and it just throws out a result in real time, whether it's in this case, whether it's a taco or whether it's an ice cream, right? Okay, so moving quickly to the next slide. There are, again, as I said, you can be predicting a class or you can be predicting a continuous number. And there are several other, facades of machine learning. So there is something called supervised learning. So supervised learning would be somewhere, when you have a class or a number to predict, right? So let's say you're predicting whether an application will get accepted or rejected, or whether you're predicting a temperature. You know that this is my dependent variable, this is my target variable, and this is what I'm trying to predict, right? So in supervised learning, you have regression, And some of the uses would be, as I said, weather forecasting, market forecasting, and population growth prediction. So these are again, forecasting numbers. So population, weather, these are all, integers or float numbers, right? So there are various sorts of regression techniques available. Linear regression is an example, or partial least squares regression is an example for this sort of a supervised learning. Or it can supervised learning can also be classification, as I said, that whether a fraud has occurred or not, yes or no, or image classification, like in the last example we saw, whether it's a taco or an ice cream. Or it can be customer retention, like whether a customer is going to leave. So if you are you work for a internet provider, or phone network provider, they would always gather a lot of data about you and understand that whether you are going to stick around or you're looking around for, so that they can take measures beforehand, and entice you with better offers so that you stay with them, right? So these are supervised learning techniques where you have an identified target variable, and you would be looking to improve on the predictions. So if a person if fraud is, let's say there's a possibility of fraud that's occurring, and you have built a model of fraud, a continuously improved model would be focusing to achieve 100% accuracy on fraudulent detections. So that would be the goal. Then there is called something called unsupervised learning. So unsupervised learning does not necessarily have a target variable, like your recommender systems. So when you are on a shopping app, they recommend products to you, right? So in this case, there is mm, no particular sort of prediction, but there is no target variable that you are targeting, or they are targeting rather. So based on your clicks, based on your past data, past history, based on your demographics, like your age, the location you're from, your sex, they would be recommending something to you. So there is no particular target variable, but it's recommender systems would recommend something to you. And then there would be customer segmentation. So these techniques, so this falls under clustering techniques. So let's say in a retail shop, there would be lots of buyers, right? So a common technique would be RFM analysis. So let's say the data scientists at the retail would be looking at the recency, frequency, monetary scores for every buyer. Like, how recently did they make a last purchase, or how frequently do they return to make a purchase, or what sort of monetary value can be attached to that customer, that how much of total purchase has the customer made in their lifetime, right? So using all that data, they would be able to assign a score to every customer that may range from, let's say, for example, 200 to 600. So using this, they can segment customers like high priority customers, mid value customers, or customers who haven't who used to purchase a lot, who have a high monetary value, but they have a very high recency score, meaning they haven't returned to the store for a long time. So in these cases, they can identify or segment the customers and give, let's say, targeted advertisement. Like, if, not every advertisement would work for everybody, right? So let's say I am a mid-value customer, and if I am looking at, let's say, motorcycles in the 2 lakh to 5 lakh range, and they send me an offer for a Ducati Scrambler, which is way more expensive. Even if the offer is good, it doesn't matter to me, because I'm not a customer of that range, right? So once they segment the customers, they can personalize these offers, these discounts, and send them across to increase their upsell, their cross sell, right? So this clustering is an unsupervised learning technique. Then there is something called dimensionality reduction, and that's a bit advanced again, where a lot of data, let's say, is collected. So there might be thousands of features for a particular record, and it's very difficult to build a model with so many features, right? So in that case, those features are brought down, some features are merged. So there are several techniques of dimensionality reduction. And finally, when we are satisfied with the resulting features, we can build a model using that. And then there is something, again, something advanced called reinforcement learning, which is mostly used in, let's say, automated parking or game AI, where good results are rewarded and poor predictions are punished more. And that's done real time. And reinforcement learning applications, as I said, they range from game AI to real-time decisions, robot navigation, automated parking, or skill acquisition, like learning new techniques, learning a game, or let's say when you play chess with a computer, that can also fall under reinforcement learning. So these are the broad techniques of machine learning. And again, elaborating a little on that. So as I said, you have supervised learning where you have labeled data. Label means yes or no or a number. And you have unsupervised learning where you segregate or where you work with unlabeled data, let's say customer segmentation, or as I said, RFM analysis, where it creates clusters of data, and let's say this customer belongs to cluster A. So cluster A customers have similar buying pattern, and cluster B customers would have a similar buying pattern among them. So the logic is every point within the same cluster is similar to each other, and points among different clusters are dissimilar to each other. So that's the basic logic. And within supervised learning, you have regression. And some examples would be the stress value of a part, or the remaining useful life of a battery, or fatigue life prediction. Or it can be classification, like whether the mesh quality is good or bad, whether the structure that you have created is stable or not stable, whether a person is eligible for a loan, yes or no, things like that. And in unsupervised learning, it can be clustering. So let's say, even if it is images, it has clustered, the screws together, and it has clustered the bolts separate, right? And similarly, there is something called association learning, like your market basket analysis or something. Like, let's say you are a customer who who is in a retail store buying bread. So if a customer is likely to buy bread, he's also more likely to buy probably tomatoes, lettuce for a sandwich, or milk as well. So the common things that you buy when you buy an item, it has if the store has 1,000 items, every item is related to each other based and given a particular score. So when you buy an item, any item, it would recommend the next top 5 items that you are going to buy. So depending on that, we can create customized offers for customers. Again, this is a slide, similar one, like the applications of supervised and unsupervised learning, and the applications of true AI, in AI in the true sense. So mostly using Knowledge Studio. I won't say it's a tool for AI applications. It's more on the traditional statistics side, and as of yet you cannot work with much. You cannot work much with image data or video data with Knowledge Studio, but you can work very well with any other sort of data, or a flat file. So in supervised learning, as I said, there would be linear regression, polynomial regression, decision trees, random forests, and then again there would be logistic regression, k-nearest neighbors, support vector machines, trees, and then in unsupervised learning there are several clustering techniques and principal component analysis, and then there are association rules. So there's several applications of ML basically. And now, again, coming to the decision making. So, firstly, you predict something. So let's say I predict that a customer is going to default on a loan. So it's a yes in the default section. And once I identify that the customer has a high chance to default, what prescriptive actions am I going to take? Whether accept or reject or give a lower line, maybe. If a customer is highly likely to default, I'll probably reject the application. Or if they have still a high chance but not very likely, not for certain to default, probably would give them a lower a lower line of credit so that the customer gets engaged, brings revenue, and also, with a lower line of credit, their chances of repayment would be higher. So that's called prescriptive action. Like once I predict, what should I do, right? So there goes your action. So this is a slide, which explains your linear and neologistic regression. So in linear regression, which is again a supervised learning technique, as you can see, there would be several data points. And in one of the assumptions of linear regression is the dependent variable or the target variable is linearly dependent on all the independent variables. And ultimately, you get the equation of a line, right? Y is equal to mx plus c. And in logistic regression, so this is the transform that you apply to a logistic regression. So y is equal to beta naught plus beta 1 x is a linear model. That's the equation of a line. And when you convert those to probabilities, this is how you convert. So your probability scores can again range from 0 to 1, right? So this is how linear and logistic regressions are linked. Linear regression is used to predict a number. Logistic regression or classification can be used to predict binary or multi-class, categories like true, false, yes, no, or class A, B, C, things like that. Then there is decision trees. So decision tree is again a supervised learning technique, and there are several calculations that work or optimizers that work in the under the hood. And in Knowledge Studio, you have CART or CHAID algorithms for decision trees, and this first node would be the root node, and everything below would be child nodes. So the more deep you build your decision tree, the more accurate your predictions would be, but the more chances of overfit as well. Like let's say if you build a decision tree which is 10 layers deep, probably it would learn a lot, or it would learn a little more than you want about your training data. So when you apply that model on unseen data and try to predict a class out of the decision tree, it would probably not perform very well because it has overfit itself. It has tried to optimize on the training data. So that part, data scientists would need to take care of, right? So that there is no overfit. Your predictions on your training data and your test data should be similar. Even if it's good in train, it should be good in test as well. Or if it's poor in train, the same should reflect on the test data as well. And this is one unsupervised learning technique, k-means clustering. So these were supervised learning techniques, and this is unsupervised learning technique where there is no target variable, but you can see that each color would correspond to a particular class of people or class of you know IDs or individuals, whatever the data points might represent, so that you identify or segregate or or segment these into separate groups. And there are several minimizing criterions available, and they would try to minimize the distance among themselves, so that each class has a very specified boundary. So it would be very difficult if all these classes were merged together huddled together, it would be difficult to differentiate them from each other. So these classes, the objective would be to very clearly segregate the classes so that the segmentation is very linear, right? So this is a real-time problem that as a data scientist you would probably encounter, like as a client who's uninitiated, and since there is an industry buzzword, they might come to you and say that we want to do machine learning, and you obviously wouldn't have any answer for it. But if they say my customer wants to do machine learning to predict time to 3D print a part, okay, now you're talking like, okay, now what's your task. And then if they say that they want to train a linear regression model to predict the time to print a 3D part based on its shape and material, so shape and material becomes the features or the columns or the independent variables, and time to predict would be your dependent variable. And if they have previous designs, that means they have previous data. You already know how much time does it take to print a 3D model, and you have rows and rows of records. So using that data, yeah, you can really build a predictive model. So now with all these talk about ML, I'll quickly show you how a Knowledge Studio looks. So this is the interface of Knowledge Studio. This is the ML platform, that we work on for predicting. And well, over here, what you see on your left-hand side are all the projects that have been built within Knowledge Studio. So for a new user, you would have nothing over here on the left side. As and when you build a project, it gets added over here. So, and these are the connect palettes, profile, manipulate, model, evaluate, and action palettes. So using the connect palette, you connect to a data set, right? Or you bring a data set or you bring a CSV file on to work upon onto Knowledge Studio. Then there is something called profile, where you profile your data. You understand how your data is distributed. You understand all the features. If there are any outliers meaning certain records that really don't add up. So if it's temperature for for the southern part of India, and you're trying to predict the temperature, and you have a lot of other features like humidity, pressure, day of the week, time of the year, and all these features, and you're trying to predict temperature, and if your prediction or if some record in the past predict shows that it was 100 degrees C on a day, you would understand it's an anomaly. It has never happened, right? So that would be an outlying record. So there are several ways to detect outliers. Yeah. So it's important to remove those outliers to better your predictions. Similarly, there is something called variable importance, variable selection, where let's say you have 10, 12, 15, 20 variables, and when you build a model, you would take the most important variables, and also it's important that each of these variables don't influence each other in your independent variables. Like if you're predicting temperature, let's say you have pressure data, humidity data. If pressure and humidity are very correlated to each other, like if pressure increases, humidity decreases, or vice versa, you can't include both the independent variables while you're building your model. So you would need to do collinearity analysis or correlation analysis for that, right? So all these are available within the profile palette. Then in manipulate palette, you have the data frame operations like aggregate, append, join, filter data, partition data, substitute missing values, or variable transformations is, something similar to compose, where you write, simple expressions. Let's say you want to take log of a particular feature because it's not very normally distributed, or if you want to standardize some features, or if you, let's say you have capital gain, capital loss, and you want to create a new feature called profit, which is capital gain minus loss probably. So a new calculated field or a calculated column, all of this can be done using manipulate. In model, these are the models that we currently have. So from decision trees, strategy tree is native to Knowledge Studio, patented. In AutoML, where you don't need to build a model, you don't need to prepare the data, it does all of that for you. Then there are bagging boosting algorithms, cluster analysis, which is again an unsupervised learning technique, deep learning models, factor analysis, PCA, linear logistic regression, your market basket for association rules, uh, stacking several models together, your ARIMA is a time series forecasting technique. Then there is the Keras deep learning or Keras forecasting nodes available as well. So Keras is a deep learning library, and you can use that library to build your models. Or scalar GLM, like when your continuous predictive your target variable is not, there is not, it's not linear, it's non-linear, right? In that case you can use PLS or scalar GLM as well. So these are the various models that's available in Knowledge Studio. Then coming to evaluate, once you have built a model, there would be certain matrices or metrics to understand, like how well your model has performed. So for that, you evaluate your model, you analyze your model. If you have built multiple models, so to predict a class, to predict a yes no target variable, you can build a logistic regression model, you can build a decision tree model, you can build a bagging boosting model, you can build a random forest model. So when you've built several models, and maybe you've built a decision tree, three decision tree models with different hyperparameters, right? Different tree depths, different number of non-terminal nodes. So each of these are singular models that are trying to achieve the same result. So when you arrive at the result, you can connect this model analyzer node to the results of these models, so that it would analyze and graphically tell you which model has performed the best among these, right? Finally, coming to the action palette. Uh, in action palette, the most useful nodes would be R code and Python code nodes, and also the scoring nodes. So if you're looking to do certain data frame manipulations using pandas, because you're used to that library, you can build bring that Python code node onto the workspace. And even let's say you feel that certain models are not included over here, you can very well import install a Python library first if you have it, and then import it over here and then work, and it would output the Python code for you. So if you wish, you can do any sort of Python manipulation over here. But if somebody is not that too proficient with the language, with R or Python, they can use the other features of drag and drop of Knowledge Studio. So this is one use case that I will quickly go through, where we have imported a data set. I'll just give you a glimpse of the data. So this is customer data, and it has about 16,500 records. And the task at hand is to predict whether each customer is going to default or not default on a particular loan. So response is the variable, is our target variable. So yes means, yeah, the person is going to default, and no means the person is not going to default. And we have other features for every customer. Apart from the ID, we have the customer's age, we have the customer's work class, we have the customer's education, we have the marital status, occupation, relationship, sex, hours per week they work, and of course the response, and capital gain, capital loss, and and several demographic features for a customer. So basically, first, to understand the data, you would probably look at, let's say if you look at age, you can see how the age is distributed. If you look at a categorical feature like relationship, you can see how it is distributed, and you gain several insights from the data, going through the data. So after that, you can do certain variable transformations. Let's see what we've done over here. Yeah, we have created a new column where if capital gain is null, because capital gain has a lot of null values. So if capital gain is null, treat it as a 0. So that's what we have done over here. So using variable transformations, you can write your own expressions. You can write your own transformations in Knowledge Studio and create new features out of existing features. Basically, once I have all my features in the data set, I partition my data into validation and development, basically a 70-30 split. So I randomly split my data, and then using the development data, I build a decision tree. And in the decision tree, when you build it, you will need to specify which is your dependent variable over here. You need to select the right one from the drop down. And when you go ahead, you can analyze each of these variables, and each variable would have an information value. So the variable at the top would have the most information value. The information value would be like how important they are to the response, like how influential is relationship to the response variable. So the ones you see at the bottom are the least important variables to this algorithm. And then if you go next, you mention these hyperparameters, like what's the tree depth, how many non-terminal nodes and terminal nodes, and these can be edited. And once you run this, it would run and it would output a decision tree for you like this. So if you go to the terminal nodes, you would be able to see most of them are homogeneous. They would be of a single color. So once it has gone through all these rules, once it has drawn a tree based on the based on the patterns, it would finally make homogeneous clusters for you. There would be some mispredictions as well, where it won't be able to classify it correctly, but that just depends on your data again. There would be always certain misclassifications. So once you have built a decision tree, all we need to see is how well the tree has performed, right? So if you go to model validation, you'll have the chance to explain that over here I am taking anything that has a probability of 0.25 of more or more as a yes. So even if the person has the littlest chance to default on a loan, I would say yes. Because let's say if I misclassify as a default, as a non-defaulter, as a defaulter, I don't have much to lose. Like I would probably take some predictive actions. But if it's definitely a defaulter, but I've misclassified that as a non-defaulter, then it would be a bad debt, and that would be a loss. So these cutoffs just depend on the use case and what you feel is important. And finally, you get the predictions, right? So the resulting data set, you can see it's 83% accurate in predicting defaulters. Means if actually the person was a defaulter, with 83% accuracy, it has predicted that the person is going to default. But we have made some compromise on in the non-defaulters. This accuracy is a little less, but this is far less important to the business. Even if, as I said, if a person is did not default or will not default, even if you classify that person as a defaulter and take some corrective actions, it would still not, you will incur a far lesser loss than if it was defaulter that's classified as a non-defaulter, right? You always want to, in this case, you would always want to avoid a situation of a bad debt. And finally, if we go and look at the data, you can see that the response prediction and the response prediction probability. So if the response, so this is the actual response. Let's bring it next to each other. So this is the actual response, no, and this is the response prediction that's generated out of your machine learning algorithm or your model. So in this case, a no has been classified correctly as a no. A yes has been classified correctly as a yes. In this case, a defaulter has been classified incorrectly as a non-defaulter. And why? Because of these probability scores, right? Basically, we are taking the action after we go through the probabilities and cutoffs. If it was less than 0.75, it would have been a correct prediction. But in this case, it's incorrect. So finally, there would be labels, whether your prediction was correct or incorrect. Wherever you see that it's a blank, means it's an incorrect prediction. And you can take certain actions if the prediction is inaccurate. You can take undersample, oversample your data set, introduce some synthetic values so that your prediction gets bumped up, right? So this is one application of, I would say, data science using Knowledge Studio, where you are trying to predict with certain degree of accuracy whether a customer is going to default or not going to default on a loan. Similarly, the same analogy can be, extended to predictive maintenance, like whether a person is or whether a part is going to, falter or, let's say if you have data of like 4 bearings in a particular machine and you are trying to predict whether that part is going to fail or not fail. Similarly, you can build a decision tree or a bagging model to achieve or to come to the result. So that's basically all I had. Finally, just as an extension of this, once you build a model, you can always generate a code for that model. So if I double click over, or I'll show you again from the beginning. So from the model, you can draw an arrow and go to action and say generate code. Once you choose this option, there are several ways to generate a code for a model. Like you can generate the code in plain English language or in PMML, Java, language of SAS, Python, R, SPSS, SQL, XML. So all of these options are available for you. And in whichever format you require the code, you can choose that and press run. So once this node is run, it would have generated the code. In this case, I chose Python. So it has generated the entire code for the model in Python language, right? So this code, this exact code can be copied and pasted and used for real-time predictions or deployment. So when you're deploying this on an endpoint on S3 or using MLOps, you can use this exact code to feed to your unseen data and deploy this model over there to generate real-time outcomes, real-time predictions. So this is taking it beyond, testing on flat files. This now using this code, you can really, use your model to make real-time predictions like anomaly detection, fraud detection, or predictive maintenance. That's all I had from my end. If you have any questions, or if you have any questions from Manoj also, you can let us know.
Hello, sir.
Yeah.
Yeah, the code that is generated, is that generated for that node specifically, or is that code generated for the like for the
Entire workflow. It's generated for the entire workflow. For the entire workflow. So up until that point, you can generate the code for any model, right? And this generate code can be connected only to a model. If it's a decision tree model or a logistic linear or a linear model, you can connect it to that model and generate the code. So the code would be generated till this point. Like it would take care of the variable transformations, the standardizations that you have done, and everything. Okay, if there are no other questions, Manoj, do you have anything to add?
I think no, Shubhajyoti. I think yeah. If there are any questions, we still have about 5 minutes. Maybe we can answer them. I think from my side, nothing else, Shubhajyoti.
Okay.
Okay. I think there are no questions. I think Shubhajyoti. So probably we could conclude the session if there are no questions.
Sure. Thank you.
Thank you. Yes, of course. And probably the recording, or if you need any details, any further details, probably you can get in touch with Ramesh and he can get you the same as soon as possible. All right. Okay, then. Thank you. Have a nice day, all of you. Thanks a lot.
Thank you all. Yes, bye.
Bye bye. Thank you.